Welcome back to our discussion on potential flow. So, in the previous lecture we started looking at the various solutions of potential flow. We are not going to spend time discussing how to solve the equation for potential flow, which is the Laplace equation. So, as I said, there are various ways of solving this. You can use separation of variables. You can take help of integral transforms, and if you were solving problems of potential flow in 2 dimension, then you can take help of analytic functions, which is basically using the Cauchy-Riemann equations that come from complex variables. So, these are not things which we are going to spend a lot of time discussing. I will just in some cases give an idea regarding where these solutions are coming from, but overall what we have seen so far is that we looked at the equation for Laplace equation, and we will focus only for 2-dimensional potential flow. So, for 2-dimensional potential flow, the equation that we are solving in the Cartesian coordinate would be of this form, or if I use cylindrical polar coordinate system, then it would take the following form in coordinates r and theta. So, based on the geometry, based on what we are trying to do, we choose either of these coordinate systems. Now, as you can see just from the Cartesian formulation, that any linear function of x or y, so if phi was some ax plus by, then that is a solution, that is a trivial solution of your governing equation, because that is a second order equation. And we saw the special case of phi equal to ax. You could do the same thing for any other linear function of y, that if you write down the velocity in the x direction, then this represents a uniform flow. So, the velocity potential being linearly dependent on your Cartesian coordinate system gives us a uniform flow, where one of the velocity component is a constant and the other is 0. If you were to choose ax plus by, then you would get a velocity field which would have u equal to a and v equal to b, which means you will get something that is like based on the sign of a and b, you are going to get something that is an oblique uniform flow. But nonetheless, a linear variation of potential with your Cartesian coordinate system gives you an uniform flow, which is a solution of your potential flow equation. We are going to look at problems in cylindrical coordinate system, and if you were to do this using separation of variables, then using separation, sorry, this should be dou theta square. So, you have a polar coordinate system where you have r as your radial coordinate, theta as your angular coordinate. So, if you solve this using separation of variables, I will skip over the exercise of how you do it. So, you assume that there is a function of r, there is a function of theta. So, if you do all of that, you will get solutions where obviously you can guess from the form of theta that there should be a solution that is some a0 theta. So, anything that is linear in theta is a solution of the governing equation. Similarly, anything that is log r is a solution. So, if you plug this here, dou phi dou r of log r would be 1 over r. So, r times 1 over r is a constant, and thus dou r of that goes to 0. So, these are the two solutions which are appearing purely as a function of theta or purely as a function of r. Besides that, you will have a family of solutions which would be a n r to the power n plus b n r to the power minus n cos n theta, and similarly you will have c n r to the power n plus dn r to the power minus n sin n theta. So, you can have, this is like a general series solution that you will have in polar coordinate, and in these are in, because this is in polar, these are known as the circular harmonics. If you do in 3D, these would be spherical harmonics. So, if you just try to see physically what do these flows look like. So, we will just take some of them, we are not going to go through all the possible solutions that are there. So, in previous lecture we saw what does q log r by 2 pi, what does this look like? So, when we calculate u r and u theta, so u r is dou phi dou r and u theta is 1 over I r dou phi dou theta, we saw that u theta was 0 for this problem and u r was q by 2 pi r. So, for this particular flow, we saw that the flow actually is radially inward or outward. So, if q was positive, this was a radially outward flow or known as a source flow, whereas if q was negative, which means the flow was rushing in, u r was negative, that was a sink flow. So, that is also a potential flow. There is flow radially coming in, there is flow radially going out. In either case, these are source sink flows, which are also potential flows. And for each case, if you want, you should always check what the vorticity is, and it should be trivially 0. That if you calculate your omega z, so omega z would be 1 by r dou r of r u theta minus 1 by r dou u r dou theta. This is in cylindrical coordinate system. So, if you plug it in, you will find that here, because u r is a function of r and u theta is 0, the vorticity is trivially 0. There is no vorticity in this particular problem. Let us take one more example that you are familiar with. So, I will consider a potential which is now corresponding to proportional to theta. So, I will just consider, I think I had B0, no sorry, I had A0. So, I will consider phi is equal to A0 theta. So, that is a solution of Laplace equation, or hence this is a potential flow, but what kind of a potential flow is this? To see what kind of a potential flow, we compute our u r. So, u r is going to be dou phi dou r, which is 0, and we compute u theta, which is 1 by r dou phi dou theta, which would be A0 by r. So, there is an azimuthal flow or a tangential flow which varies in the radial direction, and we have seen this when we got introduced to vorticity. We saw this kind of a velocity profile, a u theta that goes as 1 over r. So, this is what we called then as a point vortex or an irrotational vortex. So, where the velocity, if I were to plot my u theta as a function of radial coordinate, u theta decays as 1 over r. And if the constant, which we then realized is more appropriately written as gamma by 2 pi, where gamma is the circulation, if that constant was positive, then the spin was anticlockwise. If the constant was negative, then the spin would have been clockwise. So, a point vortex, which we already saw in our earlier discussion on vorticity, is where the vorticity is non-zero and singular at a point, and its irrotational or zero vorticity everywhere else automatically is a solution of the Laplace equation, or it is a solution of a potential flow equation for any point that is r not equal to 0. So, this is again something which we are aware of, something which we are familiar with of what this looks like. Now, you can start looking at combinations of these problems. So, consider one of the solutions that we have here. So, let us take the solution which corresponds to n equals 1. In the series solution, I will consider the case which is an n equals 1 solution. So, I will have that was B1, So, B1 cos theta by r. So, for this particular case, if I compute my dou phi dou r to find my radial velocity, this would be minus B1 cos theta by r square. And if I compute my azimuthal velocity, that would be 1 by r dou phi dou theta, which would be minus B1 sin theta by r square. So, how do these, I mean, what should the velocity profile look like? I have a radial velocity, I also have an azimuthal velocity. Both ur and u theta are present. Both decay off to 0 as r goes to infinity. But what would it look like? So, if you plot this, this will actually have a form which looks something like this. So, depending again on the sign of your B1, it will have a flow field that will look like this. Even these ones are going to close. So, eventually you will have these kind of a flow profile that it appears like this. Now, this is known as a doublet, a potential doublet or a doublet, and it is also known as a source dipole or a potential dipole. And the question is, why do we call it as a dipole? What is the reason for calling this as a dipole, and can we see this or can we anticipate this velocity profile? To anticipate this velocity profile, consider a superposition of a source and a sink. So, you have a potential that is a potential due to a source and a potential due to a sink. Both of them have exactly the same strength, and I am going to place them at a distance epsilon from the origin. So, there is a source at plus epsilon comma 0, and I have a sink which is at minus epsilon comma 0. So, what should the velocity field be for this kind of a problem? Because we said this earlier, the equation that we are solving, that is a linear equation with a linear boundary condition. So, we should be able to superpose the two velocity fields and get a solution which is a solution of the potential flow equation. At this point, we are not discussing about pressure, we are only discussing about velocity field. So, the total velocity field would be q by 2 pi. Now, the source is not located at r, because if it was located at r origin, then it would have been log r, but it is not present at the origin. Rather, it is present on the x axis at a distance epsilon, which means it would be plus epsilon cos theta. That is why where I have placed my source, and I place my sink on the other side. So, I can write this now. So, let me just make sure, yeah. So, I have placed my sink which is now on the other side. It is located at x equals minus epsilon cos theta. So, for the limit of epsilon going to 0, which means that the source and sink are getting closer and closer. So, I bring the source and sink closer and closer, which means I am going to expand this log. So, I have log of r plus epsilon cosine theta, which I could write as log of r 1 plus epsilon cosine theta by r, and I am going to expand this for small values of epsilon. So, if I do this expansion for small, so this first term would be a log r, and the next term is log 1 plus epsilon cosine theta by r. So, now if I expand this for small values of epsilon, then the term that I will get is log r plus epsilon cosine theta by r. So, now if I write my potential of the summation of the two, I have q by 2 pi log r plus epsilon cos theta by r, and the term that I am ignoring right now. That's a term that would basically be an order 1 over r cube term in that series expansion. So, I am basically expanding log 1 plus x for small values of x. Similarly, from the sinc part, I will have log r minus epsilon cosine theta by r, and then there is a correction that is an order 1 over r cube correction. So, you can see clearly the leading order contribution is cancelling out, q log r by 2 pi. What you are left with is q epsilon cosine theta by 2 pi r, and then there is a term that is order 1 over r cube. So, when you are bringing the source and sink very close to each other, if the strength of the source and sink was maintained fixed, eventually they are going to cancel each other. It is like bringing a positive charge and a negative charge, and once you put one on top of each other, then effectively it just annihilates each other. But what if you bring them closer and closer while making sure that q times epsilon. So, what is q times epsilon? Q is the strength of the source, epsilon is the distance. So, once you are bringing them closer and closer, if q times epsilon is held fixed, which is the equivalent thing that you do in charge, where you bring the two charges closer and closer, but the product of the charge times the separation is maintained constant, which is known as the strength of the dipole. So, here when q times epsilon is held fixed, you will get a potential where if I define q epsilon by 2 pi as a constant lambda, then this will be lambda cos theta by r. So, this is held fixed. So, when you bring a source and sink closer and closer, such that their strengths are also increasing. So, q is basically going as 1 over epsilon. So, they become more and more intense as they are brought closer, eventually you get the dipole picture. So, you can think of it that initially there is a sink and a source. So, the source looks like this. So, when they are far apart, the sink and the source look something like this. When you bring them closer, when the distance actually shrinks, this will transition to where there is on one side a flow that is rushing out like a source, and on the other side it closes in or comes in like a sink. So, that is why this is known as a potential dipole. So, mathematically it has a form that is cosine theta by r, but physically it is something that you get by bringing a source and sink together. And this is one of the very important solutions of potential flow, as we will see that a flow field which is given by this is actually something that is quite important in terms of constructing flow past objects. So, that was our third solution. Now, going back to the solution form that we had, that some constant r n cos n theta. We looked at the case when n was a negative integer, but if I allow n to be any negative or positive integer, now I am just going to consider n to be a positive integer. So, n will take values that are greater than equal to 1. So, if I consider them to be a positive integer, my u r is dou phi dou r, which is a n r n minus 1 cosine n theta, and u theta is minus n a n r n by r sine n theta. So, it is minus n a n r n minus 1 sine n theta. So, if you take n equals 1, what do you get? U r is a 1 cos theta. U theta is minus a 1 sin theta, which is nothing but uniform flow. written in polar coordinate. Ux equal to constant, uy equal to 0 is what you will recover from this. So, you will get a uniform flow for n equals 1. So, this is something which we have already done. We have already looked at this problem writing it in Cartesian coordinate, but it is also embedded in the cylindrical coordinate system, that n equals 1 gives us a uniform flow, streamlines which are moving from left to right. N equals 2, this is a little more interesting case. So, UR is now twice A2 R cos 2 theta. U theta is minus 2 A2 R sin 2 theta. Now, this particular case, if I now write my Ux, so I will basically use the transformation. If I write my Ux, this will be 2A2 R cos theta and Uy will be minus 2A2 R sin theta. So, you do a coordinate transformation going from r theta velocity component to xy coordinate system. So, I am just jumping over that bit and writing down what is Ux, Uy. Now, is this something that you are familiar with? Now, what is r cos theta in terms of Cartesian coordinate system? It is x, r sin theta is y. So, you have Ux is equal to a constant times x, Uy is equal to the same constant times y. And this is a flow that you have already seen couple of times already. Ux equals to x, Uy equals to minus y, that gives you a flow profile which is a family of rectangular hyperbolas. This is known as planar extensional flows, and you can always verify that for this particular problem vorticity is again 0. So, now you got a flow profile which is a little more interesting. You got a Ux which is varying with x, Uy which is varying with y, and what you have now is this planar extension, but derived from the cylindrical coordinate system. Now, you can get more interested and ask what happens if theta was n was more than 2. I mean, we do not have time to go through all values of n, but you can start guessing what is going on. So, if you see here that when n is equal to 2, then there are these two lines, the y axis and the x axis, which are your streamlines. We had mentioned this earlier, that the x and y axis are also streamlines in this problem. Now, if they are streamlines, it seems like there is a flow that is confined in the first quadrant. You can as if forget everything about all the other quadrants and think of this as a flow that is happening in one corner, right, because the two boundaries x and y axis are streamlines, which means there is no normal flow. That means this is actually a potential flow in a 90-degree corner. We did not learn it this way earlier. We learnt it as a stagnation point flow over all the ranges of x and y, but if you scoop out one of the quadrant, this is actually a flow through a corner which is of 90-degree angle. So, that tells you that the moment you make n of any other integer, automatically these are going to be flow in different wedges. You are going to get flow through different corners. So, it is a pretty complicated scenario if you think of it in terms of what you have to do. If I actually asked you solve for potential flow through a 60-degree angle, it is not immediately clear how do you go about doing something like that. It is not obvious that what exactly is to be done here, because you have two walls which are no penetration boundary condition at some angle 60 degree. So, that does not appear like there is some obvious way of proceeding at this. But now you can see that solutions of this particular form, they naturally are meant for solving problems in angles. So, when you have potential flow in angles, you can basically play around with these values of n and get a lot of various kinds of flows, some which are quite useful and some which might be more exotic. So, this is basically what you have here now for these individual flows. Now, we go back to our earlier statement. You can spend time of building these various flows, but the point that I said earlier, that if I consider two velocity potential, the sum of that velocity potential is also a solution of the Laplace equation, and that is also a velocity, gives you a flow field. So, we will do some combinations. We will again not do arbitrary combinations, we will do some motivated combinations. So, the motivated combinations I will do is I will take a flow that is obviously my uniform flow, where phi is equal to u times x, and I will consider a source flow. So, the broader motivation of doing all of this is we want to eventually know how to solve for flow past objects. That is the broader motivation of what we want to do. So, we have a potential which is u times x, and we have another potential which is proportional to log r. This is a source flow, this is uniform flow. Now, what should the superposition look like? Now, before you do any calculation, you can expect that when you superpose them, the streamlines, so what I have sketched here are streamlines. All of you should remember this, that lines of constant potential in both the problems will be perpendicular to the streamlines. These are lines of constant potential. Similarly, here lines of constant potential are going to be circular. The black lines are constant potential, the blue lines are streamlines. So, now if I were to ask what would happen to the combined problem. So, for the combined problem, you can imagine that far away it would look like a potential uniform flow when it comes from the left. When it approaches the source flow, these lines are going to get deflected. It is as if the uniform flow that is present, that does not like the flow to go through, because there is some kind of a motion that is outward here. So, it is going to deflect and it is going to itself also get swept further down. So, there should be something which looks like this kind of a picture. This is a very crude way of understanding what is going on, but it gives you a feel of what to expect, that the uniform flow streamlines, as it approaches a source, it is going to spread out. So, it is going to spread out, and the source flow, which would have otherwise moved out radially outward, cannot move out radially outward in the direction of the incoming flow, rather those streamlines are going to bend and go towards the downstream direction. So, let us now do this formally. This is basically a picture that I drew without doing any calculation. Let us try to do a formal calculation. So, formal calculation means that I have phi is equal to ux q log r by 2 pi. Now, this is a mixed coordinate system, one in Cartesian, one in cylindrical. So, I am going to write everything in polar coordinate system. So, I have this. Now, what are the velocity field components? So, ur is dou phi dou r, and that gives me u cos theta plus q by 2 pi r. U theta will be 1 over r dou phi dou theta, and that turns out to be u minus sin theta. So, I have ur component, I have u theta component, and now how do I understand this flow? So, to understand this flow, one thing which we will now look into is the concept of a stagnation point. Stagnation point is the location where the velocity is 0. All components of velocity vanish at the stagnation point. So, when you did the problem of a planar extensional flow, you saw that the origin was a stagnation point, x equals to 0, y equals to 0, this corner was a stagnation point. In this particular problem, the stagnation point is a little bit more nuanced. So, we want ur to be 0, we also want u theta to be 0. So, I will mark the location of stagnation point in polar coordinate system as r theta, r star and theta star. So, at the stagnation point, I have u cos theta star plus q by 2 pi r star is equal to 0, which means r star is minus q by 2 pi u cos theta star. And from u theta equals to 0, I have minus u sin theta star is equal to 0, which means theta star can either be 0 or it can be pi. Which means if this is the location, if this is my origin where I have placed my source, there is one stagnation point which is possible in theta, purely in terms of theta, which is at theta equals to 0, and the other which is possible at theta equals to pi. So, this is theta equals to pi, this is theta equals to 0. Now, if I choose theta equals to 0, what happens is r star is negative, because cosine of 0 would be plus 1. So, r star becomes minus q by 2 pi u, and q is positive, it is a source. So, this is invalid. So, in which case, if you are doing a source flow, if q is positive, then you have to have theta star equals to pi as your stagnation point. So, stagnation point, I will abbreviate it as SP, is theta star equals to pi and r star is minus q by 2 pi u cos pi, which is plus q 2 pi u. All of this is considering a source, because source is q0, q greater than 0. So, now that means if this is where you had your source, you are going to have a location, this is the location which is theta is pi, r star is q by 2 pi u, which means in terms of x it is 2 pi u comma 0. That is my stagnation point. So, the velocity will go to 0 here. So, I will have streamlines which will come from infinity and it will go to 0 at the stagnation point, which I will mark as S. Now, from this velocity field you can also find what is your stream function. I have written down my velocity potential, but you can also write down what is your stream function. So, stream function would be u r sin theta plus q theta by 2 pi. You can verify that u r is 1 by r dou psi dou theta. So, that gives you u sin theta plus q by 2 pi r, and u theta is minus 1 by r dou psi, minus dou psi dou r, which gives you minus u sin theta. This should be cos theta. So, u cos theta plus q by 2 pi r minus u sin theta. So, this is the corresponding stream function. So, the value of the stream function at the stagnation point So, at r star comma theta star is u r star sin theta star plus q theta star by 2 pi. Now, theta star is pi, which means this is 0. So, I get q pi by 2 pi is equal to q by 2. What's the reason for doing all of this? What is the reason for finding the value of stream function at the stagnation point? So, if I have found the value of stream function at the stagnation point, then a streamline that passes through the stagnation point should exactly have the same value, right? The value of the stream function is constant on a streamline, which means for a streamline which is given by the equation u r sin theta plus q theta by 2 pi is equal to q by 2 is the equation of a streamline passing through the stagnation point S. Because we have computed the value of the stream function at S, we first found what is stagnation point, we found what is the value of the stream function at S, and now thus we know what is the equation for a streamline that is passing through the stagnation point. So, writing it out, I have r sin theta is equal to q. So, q by 2u theta by pi minus 1, or r is q theta minus pi by 2 pi u sin theta. That is the equation of a streamline which is passing through the stagnation point. Now, how should it look like? So, as you can see that if you keep increasing your theta, as theta keeps increasing. So, let us say that you go from pi towards 1. So, obviously when you are exactly at theta equals to pi, then you get the value of r, which is q by 2 pi u, because theta minus pi by sin theta will be 1 at theta equals to pi. And then the r coordinate, if you are trying to track the r coordinate, as theta is basically going towards 0. So, make sure you are going to trace out something of this sort, because you can see that as theta goes to 0, you are going to have the numerator remaining finite, but the denominator is going to become infinitely large. So, effectively you are going to have an r which is become a very large value at infinity. Is there a sign issue? I think yeah, this should ideally be pi minus theta. Somewhere I have a sign issue that is there. But in any case, you now have the shape where you can draw the streamlines, where the streamlines are going to look like this, and in the inside you will have streamlines which will, the source flow is basically getting deflected. So, there is now this blue curve which is also a streamline. That blue curve is separating the outer region of the flow from this inner source flow. So, this is our step towards actually understanding how to build a flow that is using combination of these various potential flow solutions. So, this was just one single source flow. Now, if you think that there was a source here and you have a sink. Now, if you did not have a source, then the sink would actually bring the flow, bring all the streamlines towards itself. That is what would happen. The source is going to spread out the streamlines, the sink is going to bring them closer. What we saw here, this is a picture for a source. If you reverse the picture and you say that I am basically going to now do it for a sink, then the picture for a sink would look like this, that all the streamlines would actually come and meet at a location which is on the right of that particular sink. So, when you have a combination of the two, what will happen is the boundary will look something like this, and you will have streamlines that will go around that red curve. So, this is a potential that is given as Ux plus Q log R plus, we had I think epsilon earlier, but epsilon need not be small. So, I will just write this as a parameter epsilon by 2 pi, and then a sink which is R minus epsilon cos theta by 2 pi. So, you will have a flow around an object here. Why do I say an object? Because the red line is also a streamline, and if it is a streamline, that means that there cannot be any flow in or out of that red line. There is no normal motion to a streamline, there is no normal flow to a streamline. So, which means that by constructing the superposition of a uniform flow and a source and a sink, we are able to construct a flow field which obeys the no penetration boundary condition on this oval kind of a shape. So, this one is known as a Rankine oval, and the previous thing that we have done, which is not a complete body, is known as a half body. So, the Rankine oval is a way for us to understand how do we construct flow to satisfy no penetration boundary condition on a certain boundary. Now, this is obviously where you see that the shape of the boundary is not something that we dictated. The shape of the boundary came about by the superposition. So, you can in general try to construct these potential flow solutions and get the boundary condition on arbitrary shape boundary, but that is again something that takes a much more detailed discussion. What we are instead going to do is, we will consider the scenario of this, instead of being an oval, we will take that limit of epsilon going to 0, which means this oval is next going to become a circle. And you have already seen what happens to the source and sink pair if I take the distance between them vanishing. So, which is what we will do next. So, that is going to be a superposition of a uniform flow and a doublet or a potential dipole. So, this we will pick up in the next lecture to see that how do we combine these two and then compute the flow field that satisfies the no penetration boundary condition on a circle of a given radius A. Because currently in this particular form of the potential, the circle radius where I have to satisfy the boundary condition is nowhere there. So, we will find the strength of the dipole in terms of the uniform flow and the radius of the cylinder, and once we have the velocity field, then we can compute pressure fields and we can find out what would be the forces acting on the object. So, I will stop here.